Welcome to the first, video article. I don't know what to call these. Tutorial on how to use the 6502 board, which is a super simple single board computer made out of all real chunky components so that you can see what it does and how it works. And the idea here is that this is a board that allows you to, from absolute fundamentals, or close to absolute fundamentals, understand what a computer actually does under the hood, which can be very informative to how you think about writing programs in your other programming lives. So for starters, I'm just going to go over all of the components, the major blocks that are on this board so that you can get an understanding of what this thing even is. Firstly, it's what's in the name. The 6502 is this thing right here. So the name is 6502 Tor. I mean, you can call it 6502 Tor. You can call it whatever you want, but it's generally called the 6502. And it's a CPU that was used in a ton of 8-bit home computers from like the dawn of home computers even being a thing in the very late 70s. Through to, there were even computers up till the early 90s that were still using the 6502 that were derived from those machines before everybody started, standardizing on the IBM PC. But it's an 8-bit CPU, which means it has a data bus, which I'll get into that is 8 bits wide. The thing is, you can't do very much with 8 bits in terms of like accessing memory, because 8 bits only allows for the values between 0 and 255, so you would be able to have 256 bytes of memory, which is not very much. So when they say 8-bit, they're just referring to the data bus. The address bus is 16-bit, which means you can address about 65,000 bytes of memory, which is a lot more useful. Still not a ton in terms of today, but way more useful than 256. So that's the basic idea, and that's like almost all of what the pins on the CPU are, is that there's 8 pins on here that are the data bus and 16 pins on here that are the address bus, and then there are a couple of other sundry control signals that tell everything else how to operate, that kind of orchestrate things. But that's the idea. And so the CPU, when it's running a program, what it's doing is there's a clock, which you can see this LED here. We'll see that more in the future, but that is the clock to the CPU. And on every clock cycle, the CPU goes through a cycle of operation. Now, on the 6502, that happens to generally work out to like half an instruction. Most instructions take like 2 to 3 clock cycles, which is actually really, really efficient. Most other CPUs at this time take quite a few clock cycles to get through any given instruction. So a clock cycle, the point being, does not correspond directly to an instruction being executed. It's just an instruction may take a few steps to do all of the work it needs to do to complete what that instruction does. So your clock on here, it may be 2 or 3 clocks, this going on and off and on and off and on and off, in order for the CPU to do a cycle. But generally what that consists of is you'll have a cycle where the address pins, pretty much the first thing it ever does for an instruction is outputs the address, which we'll get into later, of the location in memory that the CPU wants to access, generally to read an instruction. And then it expects some device to put 8 bits of value on the data bus, which is just putting voltage on those wires or not putting voltage on those wires. And then it reads that, captures it, figures out what that is. Generally it's probably an instruction. Then it figures out what that instruction is supposed to do and may do another cycle where it reads maybe more data from memory to accomplish that instruction, like reading an integer, or it may write back to memory, writing an integer, which is just the same thing in reverse. Puts an address on the bus, and then it either waits for some data to be on the data pins or puts some voltage on the data pins to send it to some other chips. So I'll get into a lot more of that later on. But that's the CPU, and that's the heart of this whole thing, and I figured that's worth going into. There's a couple of things up here related directly to CPU operation. So there's this clock LED, which you will see in a little bit, and that I was just talking about. And then there's also this write LED, which is, it's kind of backwards from what you would expect. It is off when the CPU is trying to write to the rest of the hardware, and it is on when the CPU is not, which means it's trying to read from the rest of the hardware. The only other thing here is this button, which is the reset button. On mine, I modified all of these switches so that they are momentary. Everybody else will have all of these buttons are toggles, so when you press it, it turns it on and it stays on, and then when you press it again, it turns it off and stays off. So just a note, because like I'll have to hold my reset button down, for example, because it doesn't like toggle on. But what reset does is exactly what it says in the box. It's connected to a pin on the chip, and when you press it down, that tells the CPU to reset, which also takes a few clock cycles. I believe it's you have to have it happen for at least 3. If you're running the thing at full speed, like you can literally just tap it because you're getting so many clocks in a second that it doesn't matter. If you are running this thing manually, which I'm going to get into in a second, you'll have to hold that down and make sure you go through at least 3 cycles before you release this, and the CPU will start its like startup and initialization sequence to start executing instructions. So that is the CPU block over here. I'm going to move over here because this will be kind of quick to get into. This is called the glue logic. This is each of these chips implements basic logic gate, which I won't get too deep into, but there's just 3 NANDs and 3 inverters. These connect to some of the control signals coming out of the CPU and some of the control signals coming from the control section, and they go out to various devices, and basically they control whether things are selected or not. I'll get into that more in the future, not super important, but that's what that block is. Because we're near it, this shiny metal can is a 5 megahertz clock oscillator, which connects to the clock and gives it a clock, but more about that as well later. And since we're in the area, this is the RAM, which we're going to talk about a bunch today, but it's RAM. That is a RAM chip. This is a chip that stores 32 kilobytes, I believe. If I am remembering correctly, I believe it's 32 kilobytes of RAM in this chip. Technical side note that's interesting, this is what's called SRAM, stands for static RAM. And what that means is while you have this thing on, it will always contain whatever you wrote to it. It will never disappear, which may sound kind of silly. Like, it probably sounds obvious to you that if you remove power from RAM, it will lose all of its content, because that's the way that RAM works. That's why when you turn off your computer, you lose whatever you were working on unless you saved it to your hard disk, because RAM is volatile. When you turn off the power, it can't hold any information anymore. But it may sound weird to say, while it's on, it holds information, because yeah, no duh. But if you're not aware, there's another kind of memory which is more common because it's way cheaper to implement, called DRAM. And in DRAM, each of the memory locations is implemented by a little capacitor, which is just it's a circuit element that holds charge, but that charge can bleed away after a while. So because of it being built that way, it's way cheaper per byte to build, but because of that, every few milliseconds, if you don't keep refreshing the memory, it will just lose its contents. So that's a note. This is SRAM. You don't have to do anything special to keep the contents in. Like, once you've written something there, as long as the thing's on, it stays forever, which is nice. Moving back up here really quick, I won't get into it much today, but this is I'm going to call it a register. It's a 8-bit flip-flop. Both of those things may mean nothing to you, but it's a very simple output device that will allow us to store 8 bits of value from the CPU. If we write it to a specific location when we're programming, it will show up on these 8 LEDs and it will stay there. This is kind of like a 1 byte of memory that's connected to these LEDs, so you can see what it is at all times. Over here, I will really not get into it too much, because this is actually kind of neat when we get into it in the future. I'm very happy with this section. But all you need to know is that this is kind of the USB section, and mainly you've got your USB mini B connector here, and power comes in from there. So ignore everything else, that's just where your power comes in from, and this is magic mystery sauce for the moment. Which does not, for the record, while we're getting into this really doesn't affect any of this other circuitry for the most part. It's not like it's doing magic behind the scenes stuff. If you understand what's going on over here, it's not like there are secrets hidden over here. You're not missing anything, basically. Okay, so moving down, we get back into buses, and I'm gonna have to talk about buses some more. So we've got 8 LEDs over here, and we've got 16 LEDs over here, which if you were paying attention earlier, will probably make sense to you because this is 8 bytes of data and 16 bytes of address, and these are connected directly to those pins that I was talking about on the CPU. They also connect directly to the memory. These 8 pins are directly connected to the 8 pins on here, the 8 pins on here, these 8 LEDs. These LEDs are connected, almost all of these lines are connected directly to here. They're also connected directly to here. They're all shared. They all touch each other. These chips have magic inside of them. Let's just go with that until we can get into like more in-depth information about circuits, but where basically they can disconnect themselves. So even though the pins are physically connected to each other, like the chip is basically turned off, if that makes any sense. So unless the glue logic specifically tells this RAM chip, hey, you need to be reading something from the bus or you need to be writing something from the bus, it's basically like it's not connected to those wires. So that's how a bus works. That's what it is you have a bunch of things connected to the same wires, and then they can transfer stuff around because they're all connected to each other, but they're not necessarily like actively connected to the bus until something tells them to actually be listening to the bus. Except for the CPU, for the most part, which I'll get into in a second, the CPU is generally always connected to everything. But peripheral devices are generally only connected when they're asked to by the program, more or less. So that means that this always shows whatever is on the CPU's data bus, whether it's something sending data to the CPU or the CPU sending data to something. It just is putting voltage here or not, so you'll see these light up or not. And then the same thing with the address. It just will show exactly what the voltage is on these address pins, and if a pin is got high voltage on it, one of the LEDs will light up, and if it doesn't, it won't light up. Under here is some more, this is, I don't know what I would call this logic, it's gating logic, I don't know the simplest way to describe it, but more or less, these chips separate what I'm calling the control section from the CPU section. So normally, like when you're running, like, let me back up a little bit. This board basically has 2 modes. Either the CPU can be running everything, or this control section can be running everything, which means putting addresses on the bus, telling things to, transfer data, putting data on the bus, so on and so forth. And these chips are basically the thing that swap between whether the CPU is connected to all the stuff, or whether these switches and whatnot are connected to all the stuff. And that's what they do. Finally, we're getting down to the thing that I really am talking about today, which is the control section. So this is how you interact with this computer. It should be obvious because I ran over basically everything on this board and you didn't hear about anything besides RAM, CPU, and that register thing. There's no ROM on here, which ROM it's like a RAM chip, but you write data to it and it just stays there forever. And there's none of those on here. Usually you'd have one of those, like your PC's BIOS is a ROM, so that when the thing starts up, the CPU automatically starts executing out of there, and there's already data in there, so it has some code that gets it started booting up and testing the hardware and presumably looking to see if there's any disks that are like bootable, whatnot. That's not on here. You just have the RAM. So when this thing starts up, it's got nothing in its brains, ever. So how you deal with that and how you run this thing is using this control section. So generally, let's apply some power to this thing. Again, USB Mini B if you don't have yours yet. They're pretty cheap. My apologies for not sending them to people. Anyway, you just plug that in. You can plug that into a power brick or whatever you got. And when you plug that in, you should see some LEDs light up. If you do, that's good. Let me see really quick. If I turn off my overhead lamp, if you can see those any more clearly. Yeah, it's all or nothing, huh? I'll have to work on that. But you can kind of see that for the moment. So that way you're getting power and whatnot. You may have more LEDs on than this. That's, it depends on kind of how things are set up down here. So let's get into the control section. The main thing here is you've got all of these switches. And again, you've got 16 switches here and 8 switches here, so that kind of is no shocker. These are for the address, these are for the data. As a side note, I realize that some people may not be like familiar with binary or hex or things like that, and you'll kind of need to get familiar as you're doing this. I'll do that later on. Right now, I'm just kind of showing you how to physically use the thing, and we'll show how to get stuff into memory and read stuff back from memory just using the control section. We're not going to be doing anything with running any code or running the CPU today. It's just how do you use this section. And basically, you've got the switches for shoving stuff into memory, so that you can put some kind of program in there for the CPU to execute. And then you've got the clock section, which is basically controls the clock. So when this thing is running, which there's a switch here, it's called run. When it's up, it basically swaps things over so that the CPU is connected to everything and the CPU is running the show. When you turn it off, it disconnects the CPU, which is why I was saying the CPU is usually connected. It's not in this case. When we switch this off, the CPU also gets disconnected from the bus. And now the switches and whatnot are directly connected to the bus, so they're controlling the addresses and they're controlling the data. And so these switches literally, when this is down, for instance, that's a 0. When it's up, it's a 1. And that's that. So this is your address, that's your data, and I'll show you how to use this to put stuff into memory in a second. But first, let me go into, like I said, the clock section over here. So you've got the ability to switch between, am I running the CPU or am I halted and putting stuff into memory? And then you've got this switch, which is kind of your speed selector. So you'll see, let me switch up to a closer view here. It says full, slow, and manual. And right now I've got it set to manual. This selects between 3 different clock sources on the board. So manual, which it's set to right now, it's at the very bottom position, means basically this switch is directly connected to the CPU's clock. Actually, if I zoom back out again, you'll see when I am in manual mode, and I switch to run, because right now it's not going to do anything because we're not running. If I switch back to run mode, when I press mine down, clock turns off. When I lift it up, clock turns back on. And again, mine is momentary push button. Yours will be a toggle, so like if you click it once, it'll turn off. If you click it again, it'll turn on. But yeah, so it literally just connects that switch to the clock, so you can run it 1 cycle at a time using your finger as slowly as you want. The next clock source is the slow clock source, so that's the middle position. If I zoom out, you'll see things are, well, actually you can see right there, things are starting to happen on the address bus. Again, we'll get into more details about what that's actually doing in a second, but you can see it's going at a, there we go. It's going at a pretty decent clip, but we can change the speed of that using this knob. So when you turn it left, it slows the clock way down. And when you turn to the right, it turns it up so fast that you can't even see it blinking, and these LEDs are switching on and off, but you can't see it because it's happening so fast. So that's great for like debugging your code and stepping through so you can watch what it's doing, but more slowly. Because if you switch to the final clock mode, well, I'll just do it here. If I switch this to full, basically these look like they're all lit up, and that clock looks like it's just solid. It's still doing the same thing it was a second ago. It's just doing it at 5 megahertz, which is 5 million clocks per second, which is a pretty decent speed, especially for a 6502. You could do a lot at 5 megahertz. But that's what you would do when you have your program fully ready to go and you just want to run this thing full speed, which we'll do much further down the line. But for now, we'll be mostly staying in manual mode or low speed mode. So that's the clock section. Let's do the final thing for today, which is really what is supposed to be the meat and potatoes of this episode, is using this section, now that we vaguely know how to control the clock signals and how to put it between run and write mode. How can we actually get stuff in RAM now is the main point of what we're doing today. Which is funny because it's probably going to be the fastest, shortest bit at the end here. But what you do, And we're not going to describe what it is we're putting into memory. It's just going to be arbitrary right now. We're just going to be turning crap on and off, and you'll just see it go in and you'll see it come out. And then in a further tutorial next time, we will get into what that actually means, how we can use that to actually do stuff. But for now, it's just going to be googly-gook. So I, again, switched this to not run mode. This is off. So this stuff is now connected to the bus and therefore over to this RAM chip and everything else here. Basically, so right now our address is all at 0 right now, which you can also see on these. These are all off. Firstly, let's start by, if I toggle these, you can see these switches will directly correspond with these LEDs when you're not in run mode and you're messing with this. So when I turn the second one on, it turns the second address LED on. And so on and so forth. Because these switches at this point, when we're not in run mode, when we're in like program mode, these are literally directly connected over to these switches. So they're just sending 5 volts over or not. So that's what's going on there. And then what's happening right now is that we're always reading from the RAM unless we press this button, which is the only thing I haven't described yet, and this is the deposit button. So what the LEDs are showing right now is these data LEDs are actually showing something. They're showing what's in RAM. Right now this RAM is set to output whatever's on the address bus. So at address 0, which this is because they're all off, it's a 0 here. So, what if I wanted to change what's at address 0? Well, you'll see if I switch the switches on the data section, nothing changes on the LEDs whatsoever. And that's because, again, what's shown on those LEDs right now is not coming from these switches, it's coming from the RAM. But, let's say, let me just toggle in some random stuff. So I'm just gonna do an off, on, off, on, off, on, off, on, off, on. And if I hit deposit, you'll see now that shows up on the LEDs. Off, on, off, on, off, on, off, on. Because what we just did is we deposited whatever was on these switches into the location at this address in that RAM chip. And now the RAM chip, as soon as we release that deposit button, is showing what's at that memory location. So if we change the address at all, now the data is totally different. But if we go back to address 0, it saved it because, you know, memory. So just for shoots and googles, let's just write some other random stuff. So if we go to this location, and let's store all zeros. Now there's all zeros there. And if we go to this location, there's some stuff in there. Let's store all ones. Why not? Okay, now that's in there. And if we go back to 0, we have our 01, 01, 01, 01. We have our 0 at that location. And we have our all on at that location. And you can do this for all locations in memory. This is a little bit of a lie, which we'll get into later, but you can think of it as right now, more or less any setting that you have on these switches is its own unique location, and you can store something there and it will show up on these LEDs. And that's how you get stuff into RAM. And that's going to be how we program this thing. That's the entire set of controls for this thing. Like it says in the description, it's super simple, but it's also super complicated because it's so simple, because you're able to just put arbitrary whatever you want in the RAM and make the CPU do it. So the controls are relatively straightforward, but what they do is kind of fiendishly complex. Don't let that freak you out too much. I don't want to undersell the complexity, but it's also actually not that difficult to wrap your head around once you've done it a little bit. But it may, if you've never done this kind of thing, hurt your brain a bit at the start. But that's it. This just takes this and shoves it in to that location, and that's it. Okay, that is the session for today. That is how you use the control section, the absolute basics. Like I said, next time I'm going to get into a little bit more of the I/O and possibly start talking about machine code, how we actually get the CPU to start up, and how we actually get to run code on this thing. So, until next time, thank you for checking out the 65O Tutor.